Basic assumption that underlies classical mathematics is that everything is extremely regular. I mean, you reduce everything to straight lines,
circles, triangles,
flat surfaces,
pyramids, tetrahedron, icosahedron, dodecahedron,
smooth edges.
Classical mathematics is really only well suited to study the world that we've created, the things we've built using that classical mathematics. The patterns in nature, the things that were already there before we came onto the planet, the trees, the plants, the clouds, the weather systems, those were outside of mathematics.
Until the 1970s, when Benoit Mandelbrot introduced his new geometry.
Mandelbrot came along and said, hey guys, all you need to do is look at these patterns of nature in the right way, and you can apply mathematics. There is an order beneath the seeming chaos. You can write down formulas that describe clouds and flowers and plants. It's just that they're different kinds of formulas, and they give you a different kind of geometry.
The big question is, why did it take till the 1970s before somebody wrote a book called The Fractal Geometry of Nature? If they're all around us, why didn't we see them before? The answer seems to be, well, people were seeing them before. People clearly recognize this repeating quality in nature.
People like the great 19th century Japanese artist Katsushika Hokusai.
If you look well enough, you see a shadow of a cloud over Mount Fuji. The cloud is billows upon billows upon billows.
Hokusai with the great wave, you know, on top of the great wave, the smaller waves.
After my book mentioned that Hokusai was fractal, I got inundated with people saying, now we understand Hokusai. Hokusai was drawing fractals.
Everybody thinks that mathematicians are very different from artists. I've come to realize that art is actually really close to mathematics and that they're just using different language. And so for Mandelbrot, it's not about equations. It's about how do we explain this visual phenomenon.
Mandelbrot's fascination with the visual side of math began when he was a student.
It is only in January '44 that suddenly I fell in love with mathematics. And not mathematics in general, with geometry in its most concrete, sensual form. That part of geometry in which mathematics and the eye meet. The professor was talking about algebra, but I began to see in my mind geometric pictures which fitted this algebra. And once you see these pictures, the answers become obvious. So I discovered something which I had no clue before, that I knew how to transform in my mind instantly the formulas into pictures.
As a young man, Mandelbrot developed a strong sense of self-reliance, shaped in large part by his experience as a Jew living under Nazi occupation in France. For 4 years, he managed to evade the constant threat of arrest and deportation.
There is nothing more hardening in a certain sense than surviving a war, even not as a soldier, but as a hunted civilian. I knew how to act, and I didn't trust people's wisdom very much.
After the war, Mandelbrot got his PhD. He tried teaching at a French university, but he didn't seem to fit in.
They say, well, I'm very gifted but very misled, and I do things the wrong way. I was very much a fish out of water. So I abandoned this job in France and took the gamble to go to IBM.
It was 1958. The giant American corporation was pioneering a technology that would soon revolutionize the way we all live: the computer. IBM was looking for creative thinkers, nonconformists, even rebels. People like Benoit Mandelbrot.
In fact, they had cornered the market for a certain type of oddball. We never had the slightest feeling of being the establishment.
Mandelbrot's colleagues told the young mathematician about a problem of great concern to the company. IBM engineers were transmitting computer data over phone lines, but sometimes the information was not getting through.
They realized that every so often the lines became extremely noisy. Errors occurred in large numbers. It was indeed an extremely messy situation.
Mandelbrot graphed the noise data, and what he saw surprised him. Regardless of the time scale, the graph looked similar. 1 day, 1 hour, 1 second. It didn't matter. It looked about the same.
It turned out to be self-similar with a vengeance.
Mandelbrot was amazed. The strange pattern reminded him of something that had intrigued him as a young man. A mathematical mystery that dated back nearly 100 years. The mystery of the monsters.
The story really begins in the late 19th century. Mathematicians had written down a formal description of what a curve must be, but within that description, there were these other things. Things that satisfied the formal definition of what a curve is, but were so weird that you could never draw them, or you couldn't even imagine drawing them. They were just regarded as monsters or things beyond the realm.
They're not lines. They're nothing like lines. They're not circles. They were like really, really weird.
The German mathematician Georg Cantor created the first of the monsters in 1883.
He just took a straight line and he said, I'm going to break this line into thirds, and the middle third I'm going to erase. So you're left with 2 lines at each end. And now I'm going to take those 2 lines, take out the middle third, and we'll do it again. So he does that over and over again.
Most people would think, well, if I've thrown everything away, eventually there's nothing left. Not the case. There's not just 1 point left. There's not just 2 points left. There's infinitely many points left.
As you zoom in on the Cantor set, the pattern stays the same, much like the noise patterns that Mandelbrot had seen at IBM. Another strange shape was put forward by the Swedish mathematician Helge von Koch.
Koch said, well, you start with an equilateral triangle, one of the classical Euclidean geometric figures, and on each side
I take a piece and I substitute 2 pieces that are now longer than the original piece. And for each of those pieces, I substitute 2 pieces that are each longer than the original piece.
over and over again.
You get the same shape, but now each line has that little triangular bump on it.
And I break it again, and I break it again, and I break it again. And each time I break it, the line gets longer.
Every iteration, every cycle, he's adding on another little triangle.
Imagine iterating that process of adding little bits infinitely many times. What you end up with is something that's infinitely long.
The Koch curve was a paradox. To the eye, the curve appears to be perfectly finite. But mathematically, it is infinite, which means it cannot be measured.
At the time, they called it a pathological curve, because it made no sense according to the way people were thinking about measurement and Euclidean geometry and so on.
But the Koch curve turned out to be crucial to a nagging measurement problem: the length of a coastline. In the 1940s, British scientist Lewis Richardson had observed that there can be great variation between different measurements of a coastline.
It depends on how long a yardstick is and how much patience you have. If you measure the coastline of Britain with a 1-mile yardstick, you get so many yardsticks, which gives you so many miles. If you measure with a 1-foot yardstick, it turns out that it's longer. And every time you use a shorter yardstick, you get a longer number.
Because you can always find finer indentations.
Mandelbrot saw that the finer and finer indentations in the Koch curve were precisely what was needed to model coastlines.
He wrote a very famous article in Science magazine called "How Long is the Coastline of Britain?"
A coastline, in geometric terms, said Mandelbrot, is a fractal. And though he knew he couldn't measure its length, he suspected he could measure something else: its roughness. To do that required rethinking one of the basic concepts in math: dimension.
what we would think of as normal geometry. One dimension is the straight line. Two dimensions